So covalent bonding, we've already put a definition down, is when two nonmetals come together and they share electrons. Nice sharing. I've already indicated to you that it's not quite as nice as that sharing model. We looked at that term called electronegativity, which talks about how strongly an atom pulls on an electron when they're forming a bond or they're sharing. It's kind of weird. We talk about how much they pull when they're sharing. It's not really good sharing in any way. And that's what we want to talk about today. And so we've got a lot of information that we've got to cover concerning covalent bonding. Number one, we have to talk about what a bond is and what a single bond versus double and a triple bond is. And then we'll look closer at this sharing. Because up to this point in time, you draw a bond and you think of two electrons there, nice equal sharing. But we've already seen a glimpse that the sharing isn't always equal. If I put a chlorine atom up against a hydrogen atom and form a bond, we've already seen that the chlorine has a higher electronegativity, and therefore the sharing isn't equal, and that does something to the bond. It changes it. So first we will be going over all that good stuff on how to draw Lewis diagrams with all the lines and the dots, but then we will be delving a little deeper in those bonds and taking a closer look at exactly what's happening in that bond when it comes to those electrons. How good are they sharing? All right? So let's first define a few things. Let's not write like mad here. Let me just check that, make sure that these are good. Yeah, I do want this slide written down. Again, I find sometimes our PowerPoints are too wordy. That's why sometimes I tell you not to write some of the stuff down. And that's a good skill for you to kind of build on, to try to critically think about what is good information and what isn't, all right? Again, another good skill that you could work on is, instead of writing it all down, quickly read it. Contains two or more nonmetals joined by a covalent bond. You might even be able to simplify that down to two or more nonmetals, right, joined by covalent bond. You see what I mean? Sometimes you don't need all that those extra words to get the concept, all right? When you go to study, that's also an important thing. Go through your notes and get rid of all that extra information, all right? Sometimes young students are overwhelmed by their notes. Read them through and distill it down to the essence of what you need to remember so you can get that all in your head. Smallest part of a molecular substance that has the properties of that compound is called a molecule. So we talk about water molecules, but we don't talk about sodium chloride molecules. Sodium chloride is ionic, and so it has that crystal structure. We call that the formula unit, the simplest formula that represents that ionic substance. But molecules are different. Molecules have distinct beginnings and ends, and therefore can be considered one entire little unit, a molecule, where ionic compounds cannot be considered that. And so that's what we're going to be talking about now, these molecules, these chunks. Again, I looked at the slides this morning. There were some of them that I didn't think needed all to be written down. You know what? This is exactly an example of that, all right? Let's not write this down. We're going to look at all kinds of molecules when we start drawing them. And diatomic molecules, di means it contains two different atoms. That's not too surprising. I don't think we need to write that. Now, we can have diatomic elements, H2, N2, O2, F2, Cl2, Br2, I2. And those are all, and we talked about this yesterday, somebody mentioned it yesterday in the other class, but we've got to be very careful with this. Those elements are all what we call the Hofbrinkel elements. Have you heard that before? I thought that was the craziest thing in the world. Mr. Williams brought that when he came from wherever he was teaching. And all of a sudden, students started to talk about the Hofbrinkel ones. and they started to make reference to Hofbrinkel the clown, and I said, what the heck are you talking about? That's the craziest thing I'd ever seen. And then they described to me this picture with this clown holding all these balloons and all of the gases that had to be diatomic. I guess it works. I got some issues with it. Hydrogen is really the only gas out of all of the Hofbrinkel gases that is lighter than air. So to make it correct, only one balloon should be floating. The rest of the balloons should be hanging towards the ground. That's just me. I'm a little picky when it comes to stuff like that. Yeah, when we watch movies and some physics is really bad, I can't handle it. Anyway, the Hofbrinkel is a good way to remember it. And keep in mind, that's only when those elements are in the gaseous state. H2, N2, O2. So I'm talking about hydrogen gas, nitrogen gas, I2, Br2, etc., etc. Anyway, we'll deal with that a little bit more later on. Other diatomic molecules, HCl, CO, obviously. And if we've got more than two molecules bonded together, then we've got polyatomic molecules. There are some elements that exist as more than two bonded together. Solid phosphorus is actually P4. Solid sulfur is actually S8. The 8 S's are actually in a crown orientation. It makes this little crown shape. We're not going to be using that in this course. When I talk about phosphorus or about sulfur and I want you to put a formula down for it, you'll just put P and you'll put S. For these guys, though, I've got to have them as H2, N2, O2, F2, etc. And obviously, we can have lots of polyatomic molecules that we'll be looking at, and all they are is essentially examples of where they have more than one atom in the molecule. Not useful in writing down at this point. How do metal and non-metal atoms bond? This is good information, all right? This again now relates our electron affinity to the fact that they form a bond and that they share, all right? And notice I've got share in italics there because by the end of our discussion on molecular compounds, you will have learned that it's far from sharing. So again, as we talk about sharing electrons, I'm sure of it in your mind right now. You're imagining two atoms with one electron, and it finds another atom with one electron, and it says, you want to share? And you're probably even imagining those two atoms holding hands, such that they each have an electron in their hand, and they go on their way all happy. It would be beautiful if that were the case. But in reality, let me start with the simplest example. H2 looks like this. We're going to draw that picture in a moment, but you've probably seen a picture like that before. And you might even be imagining right now that that line is representing their hands. They're holding hands. Oh, it's so beautiful. Again, what's actually taking place, we have the nucleus, and in that nucleus is an electron. And for the other hydrogen, I'm going to draw it over here, it has a nucleus, and it has an electron. I'll draw it down there. And this electron is going to be attracted to that nucleus. Opposite charges attract. In this case, we would call this the electron affinity for my yellow atom here. It's pulling on that other atom's electron. This electron here is going to hang on to its own electron. Or sorry, this proton here is going to hang on to its own electron. The exact same thing will happen on the other side. We'll have an attraction here and an attraction there. And with all of these forces pulling back towards each other's nuclei, that causes the two atoms to simply stick together. They come together. That's as fancy or romantic or holding hands as it gets. They aren't actually, holding hands. They're just coming together. All right? Now, it turns out that we have theories beyond this simplistic view of them coming together. In grade 12, you'll learn about molecular orbitals as opposed to atomic orbitals. And you'll learn about how these molecular orbitals have all these cool shapes and how we've theorized and we can theoretically explain the shape of molecules. And we can actually look at molecules using something called neutron diffraction and X-ray diffraction. And the molecules look exactly the way these theories predict. So there are higher levels of theories that go with this, and you'll learn this if you take grade 12. But for now, you need to think of a covalent bond as simply two atoms that have an attraction for their neighbor's electrons, but also have an attraction for their own electron. And what does that do? It brings them together. All right? Now, we've learned that when they come together, those two electrons spend a little more time in between the atoms, and so we draw a bond that represents why they're being held together. But they're simply being held together because of these opposite charges attracting each other, and because they won't let go, they have to kind of hang out with each other. They simply have to get together. Okay, so covalent bond, let's define this. This is good information as well. So what we need to do now is define this relationship that they've kind of formed, where they're kind of just hanging out together. Why? Because they're not going to let go of their own electron, and they've got to pull on the neighbor's electron. Let's define this thing. So again, we bring the term shared pair. I just told you it's not sharing. I told you it's really a tug of war. But we keep that, we always keep those words that we kind of have learned from. But just keep in mind, they're not really sharing. They are kind of coming together. They're hanging out with each other. And they hang out in such a way that we can explain things better if we think of it as sharing. So really the word share is to have us explain it in our minds easier. So we say they share. And we consider the electrons to belong simultaneously to both. Again, as if it's the greatest international deal ever. Hey, let's share our electrons. You come right up beside me, and we will pretend that we both own these electrons. Now, in a moment, we're going to start drawing some Lewis diagrams to represent these things. And we're going to be putting bonds on them. Those are the lines. And the number of covalent bonds that a nonmetal can form equals the number of unpaired electrons it has in the valence shell. So we're going to have to keep in mind how many electrons that they have. Again, we're looking now solely at nonmetals. So we're looking at the fact that, like fluorine, chlorine, bromine, it's missing one, so it can have one bond. Oxygen, sulfur, selenium can have 2 bonds. Nitrogen, phosphorus, arsenic, 3 bonds, 4 bonds. All right? Boron is a special case. We are not going to be touching boron compounds in this course because we've got to learn a little more detail before we can explain that one. No, boron does not create 5 bonds. It doesn't have enough space to do that. It doesn't do that. All right? So we'll just ignore boron. Okay. So let's start drawing some covalent bonds. We're going to start with the simple ones, single covalent bonds. I'm going to be introducing you to some ways in which we draw these structures. So that on a test, you'll know if I ask for a particular type of diagram, you'll know what I'm looking for. And we also need to kind of interpret those pictures so that we can judge whether we've got the diagram correct. So a single covalent bond is formed when two atoms share two electrons and each atom contributes one. It's like that perfect sharing deal. Hey, you want to share? I've got one. Good, I've got one too. Perfect. Single covalent bond. The example I'm going to do is a hydrogen molecule. All right? And that's H2. The simplest molecule we can come up with. I'm going to start by drawing an electron dot diagram. But once we get good at this, we're going to roll past the electron dot diagrams, and I'm going to want you to kind of be able to get right to the Lewis diagram right from the molecule. So this electron dot diagram is just to kind of give you a starting point. The electron dot diagram, H with one electron, H with another electron. We can represent an electron by a little X as well as a dot, just so that we can differentiate between the two electrons. We're going to bring those two things together. Oh, it's perfect. Dot X with an H. Isn't that lovely? Because hydrogen is a special case and it only needs two electrons to have a full outer shell, we would say that those hydrogens are happy, right? They're not really happy, right? But they got a full outer shell. Again, we still go back to that. The Lewis diagram is different from the electron dot diagram in that we switch out the shared pair of electrons for a line. H, single bond, H. This is nothing new, I don't believe. Is that correct? Just to define it here, I'm going to use a different color. This is a single bond, all right? And inside that single bond are two electrons. When you're telling me how to draw things, when we go and do some examples, you would say to me, H, single bond H, and when you say the word single bond, I know to put a line. You see what I'm saying? That's kind of the way we talk about it. You wouldn't say H, horizontal line H. Say H, single bond H. Okay? When I look at this picture, and I'm asking my question whether hydrogen is happy, I see that line. In my mind, I'm thinking two electrons. There's two electrons around that hydrogen. That's a happy hydrogen. That's a good picture. Okay? Let's keep going. Do some more examples. Let's do now a chlorine molecule. If you're seeing where this is progressing, by all means, go ahead of me. You might not be able to do the structural diagram. I have to define that for you. So the electron dot diagram contains all of the electrons. Chlorine, oh, I like yellow better. Chlorine, 1, 2, 3, 4, 5, 6, 7. You'll notice I've put the lone electron on the right-hand side so I can bring it together with the other chlorine's electron. You can manipulate where that lone electron is. It doesn't have to be in the same spot all the time. Other chlorine, 1, 2, 3, 4, 5, 6, 7. Oh, they're going to get together. It's absolutely perfect. 1, 2, 3, 4, 5, 6, 7. Cl 1, 2, 3, 4, 5, 6, 7. And that is the electron dot diagram for the chlorine molecule. I can now substitute that pair that's in between the two atoms with a line to make the Lewis structure. Cl line, Cl, 1, 2, 3, 4, 5, 6. And because I don't need to differentiate now, I'll make these dots as well. The electron dot diagram is all dots. So I guess we could say these are all dots. The Lewis structure is dots and lines. All right? And when we do a structural diagram, we don't care about those extra electrons that are on the end. We know they're there, but because we've been doing chemistry for many, many years, okay, that's you in the future, but because we've been doing chemistry for many, many years, we don't worry about these, so we draw the structural diagram like this. All right? And the structural diagram is just lines. Those are really simplistic definitions, but they get the point across. Let's go back and look at the Lewis diagram for a moment. I said to you when you were drawing Lewis diagrams for the ionic compounds, the most important thing is that you don't create electrons out of nowhere and you don't have electrons disappearing out of nowhere. So the most important thing in your Lewis structure is that you've got all the electrons accounted for. How many electrons do we have in total at the beginning before we create our picture of Cl2? How many valence electrons are there available for bonding? Chris? 14. 7 times 2. Check your picture in the end. Make sure you have the right number of electrons. 2, 4, 6, 8, 10, 12, and how many are in the line? So 14. So I've got a picture that I haven't lost any electrons. I've got everybody accounted for. That's a good little check. Another thing to check for is you're going to find that things will bond so that it gets a full outer shell. Again, we're making it sound as if they're, they got brains and they're happy to get a full outer shell. And I'm going to use that terminology. The physics just works such that when we observe these things, it appears that they want a full outer shell. So that's the other check. 2, 4, 6, and if we consider this to belong to this Cl, 8, 2, 4, 6, 8, those are happy chlorines. So we've got our chlorines with full outer shells. We haven't lost or gained any electrons. That's a good Lewis structure. So it's always good to do a quick check when you're done to make sure everything's happy and we haven't gained or lost any electrons. Let's do some more. Really? Shut it off. Put it away. First warning. Fun stuff. Little rule here called the octet rule. And this is that second part of the rule that I just mentioned to determine whether it is small font there if you're visually slightly impaired. Non-metal atoms. You're good to go? Will share electrons in order to get 8 in their valence shell. The exception is hydrogen. It'll share to get 2. It's called the octet rule because they tend to make bonds such that they have 8 electrons around them. And that's a check. You should always be doing 2 checks. Total electrons and the octet rule. And that will determine whether you have a good Lewis structure or not. Yep.
I wondered why the first one is 2 and 8.
We do know this. Bohr's rule determined this. That's that 2n squared equation that we learned way at the beginning when we were talking about that. And when we talk next year about what is called quantum theory and quantum orbitals, it works perfectly. It can be explained with about 4 or 5 rules that govern what the shape of the orbitals are and all these sub-levels I've been talking about, once you put those rules into place, and the really laws of quantum physics, it all falls out. It all just, the numbers work perfectly. So we do know, and I can't tell you right now, because it would take about 5 lessons. But come back in grade 12 university, you'll be able to get this all figured out. Okay, let's do a few more of these. HCl. You know what? I think, actually no, you do that yourselves and we'll take it up. Notice when we did the diagrams for ionic compounds, right, we would draw our two things, and then we traded electrons. This time we don't. We just bring them together. They're attracted to each other. You go ahead, try to draw the Lewis, try to draw the structural diagrams. In a moment, I'm going to ask you to describe it to me. We already know how to describe a line, that's single bond. The way you describe these pairs of electrons, we call them lone pairs, all right? So we could say that chlorine has 3 lone pairs. They're pairs that are by themselves, pairs. These are lone electrons. Singles. These are lone pairs by themselves, but they're pairs. So if we call these lone pairs and we call the line single bonds, somebody tell me how to draw the Lewis structure. I don't even care about this one. You've already brought it together. Somebody tell me what this one is. Yep, what do you got, Dallas? I want you to tell me exactly the picture that you have on your paper right now for Lewis structure, and you just read it off. You can say H or you can say hydrogen. Have you got a picture under Lewis structure? Well, then you can't answer my question. What do we got there, Emily? H single bond, chlorine with 3 lone pairs. And that describes the thing perfectly. All right? H single bond and 3 lone pairs on the chlorine, perfect. All right? So that came from a hydrogen bonding together with that chlorine. It still has its pairs, and now it's a single bond. And what's the difference between the Lewis structure and the structural diagram? Emily? Get rid of the dots. It's that simple. HCl. Structural diagram gives us the essence of the structure without all those extra dots to worry about. Let's do a bunch more. Actually, first, we're going to kind of summarize the number of bonds we can have. Yeah, let's write this down. It doesn't need to be in a big table, but this is good information. This is good information. Sometimes I've wanted to kind of squeeze it down a little bit. But I need you to be able to understand going from the atom to the diagram. And you know what? I'm actually going to change number of bonds. Yeah, I'm going to change the number of bonds. And I'm going to put that as, I'm going to put it as Lewis diagram. Because I find this is better if it's visually represented than just writing down the number of bonds it can have. And then I just forget to change my PowerPoint, so I just have to fix it every time. And we're going to start down here at hydrogen. We're actually going to fill in hydrogen first, because we've seen hydrogen. What I want to do is, I want you to be able to visually in your mind, when we talk about a chlorine or a sulfur or nitrogen or phosphorus or silicon or whatever, imagine what it's going to look like in the Lewis diagram. How many lines should it have coming from it? How many dots should it have coming from it? Because then when we start to draw Lewis diagrams, you can think of that visually in your mind and you can start putting it together. Really, covalent compounds are very much like putting Lego together, all right? And you simply put the molecule together based on how many connections things have. So that's what we're looking at. How many connections do each of these things have? How many valence electrons in hydrogen? Chris? One. One valence electron. One. Right? We could even draw a picture of it. H. So how many unpaired electrons are there? How many are not paired up? One. Which means it's going to be able to form one bond. Which means when we draw the Lewis diagram for hydrogen, it's going to look like this. It's going to have one line on it and 0 lone pairs. And that's the way we need to visualize it in our minds when we draw it. Group 17, how many valence electrons? Yeah, that was 7. 7, and I'm going to use Cl as my example. 1, 2, 3, 4, 5, 6, 7. How many unpaired electrons does it have? Yep, 1. And therefore, it also can only have one line coming from it. But it's going to look different. It's going to look different in that it's going to have one line and 3 lone pairs. And all of the atoms in group 17 should look like that when you bond them with something in a covalent bond. 16, valence electrons. Just spit it out. 6. What should I use as an example? You guys pick. Sulfur. That's a good one. Sulfur. 1, 2, 3, 4, 5, 6. How many unpaired electrons? 2, which means it can form 2 bonds. And so when you see sulfur, it's going to look like this. All right? 2 bonds and 2 lone pairs. But it could also look like this. What do we call it when we put the 2 lines together like that? Anybody know from last year? Emily? Oh, she lost her voice, but I could read her lips. She was going to say a double bond. And that's correct. So I'm looking ahead. We haven't talked about double bonds, but what I'm saying is sulfur could look like this or look like this. Okay? 5. What's my example? What do you want? Pick a group. 5. 1 element. Nitrogen. It's a good one. Nitrogen. How many dots does it have? 5. 1, 2, 3, 4, 5. How many unpaired? 3. How many lines does it have coming from it? 3. It is that simple. Nitrogen. So it can have like this. All right? But it can also have like this. A double bond and a single bond, and a lone pair. Or, what's the extreme here? What could it have? A triple bond. So your nitrogen could also look like this. And I'm running out of space, but 1, 2, 3, that's a triple bond. And then the lone pair goes on the back side, actually. That's because I know the shape of these things. You guys don't know the shape. If you didn't put the lone pair on the back side, I wouldn't care. All right? Next year you'll learn that. Group 4, how many valence electrons? 4. Example? You're gonna go with gallium. You're gonna go with lead. Yeah, really? Carbon, people. It's the only game in town. Silicon doesn't really do much of this. Number of unpaired electrons? 4. How many lines are coming from carbon? 4. 1, 2, 3, 4. Now it gets fun because I got all kinds of options here. What else could there be? What other orientation could I have other than 4 single bonds? Yep. I could have 2 double bonds. And you know what? This box is going to get full really fast, but I'll put here the 2 double bonds because that's a good example. Let me just put here an etc. Somebody else tell me another orientation it could have. Yep. No, it can't have a quadruple bond, actually. That's a nice try. Quadruple bonds don't exist. And when I get to the end of my lesson on triple bonds, I'll tell you why that is. But that makes good sense. But I can't have a quadruple bond. Yep. Single bond and a triple bond. What else could I have? Yep. Two singles and a double. Okay? So those are all the different orientations that we could have for our carbons. Okay, now let's start drawing some diagrams. Hold on one second. Don't write this down. Don't write this down. It's online. All you got to do is stick your atoms together, all right? And it says here, the one with the highest valence as the central atom. The one with the most arms coming off of it has to go in the center. You're never going to put hydrogen in the center. Surround the central atom with the other atoms. Join each atom with a single bond. Add bonds to satisfy the bonding capacity. Add lone pairs to complete the octet rule. This is a better example of just do than write it down. And now I'm just asking for Lewis diagrams. Selenium. How many lines coming from it? 2. Oh, I've got 2 H's. That's pretty handy because it only gets 1 line. Go ahead, don't wait for me. Put a selenium, draw a couple of lines, bond it with hydrogen. What's the only thing that's missing on the selenium? If I just draw my selenium, Se, put a couple of lines on it with some H, my picture isn't quite done. What do I need? 2 lone pairs. Now I'm going to put it top and bottom just because I put the lines that way, but I could have made it like an angle and put them off to the side. I don't care about the shape for you guys. I'll be teaching you shape next year. All right? Excellent. That's a good Lewis diagram. We could make sure that the octet rule is satisfied. Is selenium happy? Yeah. Are the hydrogens happy? Yes. The other rule would be make sure we didn't add any electrons. Sulfur has 6 valence electrons, right? Hydrogen has each 1. So that's a total of 8, right? Do I have 8 electrons in my structure? Excellent. That's a good structure. You're done. You've done it. Yeah, don't mind that chart. We used to teach it by, doing the number of bonds things. I want you to think about what they look like. You could still look at it if you want to get some information off of it, but I want you to think of a nitrogen. I want you to go to here, think about how many lines it's going to have, how many dots it's going to have, build your structure. So like I said, this is now more like building Lego than thinking about atoms. Certain atoms have certain numbers of connections. You need to simply put your molecule together such that the connections are correct and make sure you've got all your electrons counted for. Don't wait for me. And pencil's a good thing. And when you tell me how to draw it, you can either say N or you can say nitrogen, or you can say H, or you can say hydrogen. You're going to tell me the next one there, Dallas? 3 single bonds. I know what that means. So there's 3 single bonds to hydrogen. Okay, I can draw that. That makes sense. On the top of which? Nitrogen. Excellent, thank you. Do you see what I mean? Because if you put it on the hydrogen, whoa, that's not the right picture. Exactly. Do we have a suggestion for how to draw the last one? Yeah, what do you got there? Carbon. 4 single bonds. for each one, I assume? Because that's the only atoms I got. Yep. That's a good structural diagram, but I want Lewis diagrams. So I need all the dots. Jory? 3 lone pairs on each chlorine. That makes good sense to me. I can do that. That's a good picture. All right? We could total up the electrons, but that looks good. Are the chlorines happy? Is the carbon happy? Good. Then it's a good structure. Double covalent bonds. Did I move too quickly there? Did everyone get that picture done? We're good? Let's now talk about double bonds. I've already kind of alluded to you how we draw double bonds. We just bring the 2 lines together. I've left some blanks in here. Make you think a little bit. Double covalent bond is formed when 2 atoms share blank electrons. I'm looking for numbers, by the way. And each atom contributes blank electrons. So how many electrons are being shared between the 2 atoms, and how many does each atom contribute if it's a double bond? Yep. Yeah. Shares 4 electrons, and each guy contributes 2. Still a pretty good share deal. We're talking about sharing. Normally, I would start with the electron dot diagram, but I'm looking at the clock and I'd like to try to get to the end of triple bonds. So let's go straight to the Lewis diagram. Lewis. I know if I advance the slide one more, it'll put on electron dot diagram and Lewis and structural. But let's jump ahead. How many lines have to be coming from each oxygen? How many bonds come from each oxygen? It's got to be 2. And I have 2 oxygens. Can somebody think of a way to draw this thing and everything be satisfied? Yeah, what do you got? Oxygen, double bond, another oxygen. How many pairs? I want 3 pairs on each oxygen, 2 pairs on each oxygen. 1, 2, 3, 4, 1, 2, 3, 4. If you're ever questioning how many pairs, right? How many valence electrons does each oxygen have? 6. So if I've got 2 oxygens, how many electrons should I have in total in my picture? 12. I should have 12 electrons. 2, 4, 6, 8, 10, 12, right? Because there's 4 electrons in there. If I had those other electrons on it, right, I'd then have way too many electrons, right? Even if I put another 2 electrons, let's say I put another 2 electrons there, how many would oxygen have in total around it if I had 2 electrons there? 10, and that would break the octet rule. So I can't put any more on there. I just want to put a little definition here. That little thing is what we call a double bond. I think you know that already, but I'll just make it official. And in that thing, there are 4 electrons, but I like to think of like each line as being 2, and so then I count it as 2 and 2, right? You can get that. Okay, let's draw some pictures that contain some double bonds then. Oops. There's 2 of them. Now this is, well, I think we encountered more than that had, more than one. Which one's going to go in the center of this, of CO2? What's going to go in the center? Yeah? Yeah, got to have carbon. Why did you put carbon in the center? That's a good way to start. That's not bad, because it is a balanced picture. But what other reason would we use to put it there? It has the most bonds, so it's going to be able to make the most number of connections. You typically put the one with the most bonds in the center. Now this one here is going to have, it doesn't really have a center, because it's going to have 2 centers, because we're going to have to put the H's on there in such a way. So this one's a little trickier. but it must contain a double bond. All right? Does somebody have a suggestion for the first one? What do we got for CO2? Chanel does. You got one finished. What do you got?
Carbon has double bond.
Yep. Mm-hmm.
And they each have
Very nice. Checking the octet rule. Everybody's got 8. Everybody's happy. Now with this type of thing, it becomes tricky, but we can do it. Some of you may have it done. Does anybody have an idea? Anybody have them done? You got some ideas? Excellent. For those who are struggling, you could always do this type of thing. And this is a little rudimentary, maybe something you do in grade 10, but you know what, it still works. You could draw all your C's, C and C, all right, and then draw your H's, 2, 3, 4, and then you could start visualizing and asking yourself how we're going to make them connect. You could think that you could stick these H's all on one, but then I've only got a single bond here on the carbon. I need to somehow make 2 connections, so I might do something like this. There's a connection, and I could make another connection there. Now, you're not going to actually draw it like that. In the end, you'd swing them around to make a nice picture, but at least you could visualize the connection starting to develop. Then you can see, oh, look, I've got 2 openings here. I got to take it to, oh, 2 openings here. Oh, I see it. I got it, right? So if you're stuck, you could always, doodle, separate them out, start connecting them with crazy wonky lines until you make the bonds. All right, I'll take a suggestion from someone who's got it. Abby, what do you got? Yep. Yeah. And that's on both. Yep. And are there any lone pairs? No, there's no lone pairs on carbon. Is everybody happy? That's a good Lewis diagram. So if you find you're getting stuck, even if you did that, the same thing with the, let's say you did this type of thing, carbon and then oxygen, right? And then oxygen, you may not have oriented it this way, but as soon as you start doing that, you can start thinking, okay, oh yeah, I can see a connection here. That's a funny looking carbon dioxide molecule, but that would start getting you thinking about how to draw it, all right? Oh, let's do a couple of more fun ones. Done already? Oh, you're thinking. All right. Okay, what do you think? Haley, what do you got back there? You got a picture for this one? Know where to start? Did you put your separate pictures down, start to connect them together? Jory, what have you got? You got a picture for that one? All right. Hydrogen? Okay. Okay, so you've just drawn some hydrogens. Excellent. You want to put a carbon next. How many lines come from it? 1, 2, 3, 4. And how many lines come from it? 3, and a lone pair. And I think we need one more hydrogen somewhere, don't we? All right. Well, this is in the lesson on double bonds, so I'm going to have a double bond in there. Any ideas on how we can connect these things? Jory, you want to keep going?
Not really.
Well, we need to start connecting somewhere. You got to dive in on these. What do you think? Yeah, go ahead. So double bond the carbon to the nitrogen, make a couple of connections there. Put the 3 hydrogens on 1 nitrogen. I've only got 1 connection left on the nitrogen. I can't put 3 hydrogens on the nitrogen. I've only got 1 connection left on that nitrogen. I can't put any more there. Yeah, Jory? Yeah, I could. I could just do that. Now I could do that for the other one. I'll connect this one to here, and that's the picture, but it's really ugly. Now we just have to clean it up. So now we got to clean that up a little bit, bring everything in tightly, put nice double bonds in there. So this time, so somebody tell me how to do this without this mess. Atlee, what do we got? Carbon, double bond nitrogen, single bond hydrogen, two single bonds to hydrogen, lone pair on nitrogen. Good picture. Okay? So you've got to dive in. If you're not seeing these, and you know what, I'll tell you right now, if I pulled the room, I got people in the class right now, they're looking at that H2CO and they're looking up in the air for 2 seconds and they draw it perfectly. Bang. And there are people in this room that are looking at that going, okay, whoa. And that's fine. That's the way this type of thing is. But go back to the basics. Now, if you're still struggling with the fact that O is going to look like this, you need to write that down somewhere and memorize it. All right? Or you need to remember how to get that off of the periodic table. 6 electrons in the outer shell. 1, 2, 3, 4, 5, 6. Those lone guys, 5 and 6, they end up getting the lines. So you've got to be able to go from there to there. Carbon, 1, 2, 3, 4, because it's got 4 all by itself. 2 hydrogens, and then you need to start sticking them together. And Jory's gaining confidence because now the hand is up. Are you telling me the final structure? Fabulous. Mm-hmm. Mm-hmm. Excellent. Okay? So again, those of us, right, starting to see this and this, that's not really a proper diagram, but it'll do. And then this, and that's obviously the same as that. Like, come on. It's easy. Okay? All right. Oh, and we were right on top of a bell, aren't we? We're not going to be able to get to triple covalent bond, which means I can't give you any homework at this point. So there you go. But what I do want you to do is if you're still struggling on how many lines these things are going to have from it, go back and look at that. Memorize that stuff. That's the beginning of everything. All right? You could even make up some of your own if you'd like. If you wanted to make up some practice problems, all you got to do is put them in combinations such that they fulfill that that requirement.
I went on the
Yep.
note from Monday.
Yep.
And I couldn't find the note, and I clicked on the video.